And our final talk for today is by Walter Robinson and Jimmy Booth. It's How Will Storms and Storm Tracks Change? Again, extratropical cyclones on a warmer Earth. Dr. Walter Robinson is a professor at North Carolina State University. His research is focused on large-scale atmospheric dynamics and the dynamics of the Earth's climate, including climate variability and climate change. Jimmy Booth is an assistant professor in the Earth and Atmospheric Sciences Department at the City College of New York. His research interests include mid-latitude atmospheric dynamics, air-sea interactions, and moist processes in extratropical cyclones. And knowing both of these people, what I can say about them is they both have an excellent understanding of both the theoretical aspects of cyclones and cyclone development, and also a practical feeling for what actually happens in the real world. So thanks, guys. Thanks for this talk.
Well, I guess I'm going to go first. This is Walt. Thanks very much, David. It's fun to be doing this. I think while the title slide is, we'll move ahead in a second, I think the key issue for this problem, and we got the sense of that from Tim's talk, is we have these competing effects. A climate where the main source of energy for these storms is the equatorial pole temperature gradient that we expect to get weaker. But they also, these storms, these mid-latitude storms, just like tropical storms, get energy from rainfall, from latent heat released in rain. And we expect the atmosphere, as they say, to become juicier that will tend to make the storm stronger. So Jimmy's driving the slides. If you would go on to the next one, Jimmy. There we go. Okay. So we wanted to go back, and it was actually fun writing this chapter and working with Jimmy on it. We wanted to go back to the very beginning. And what are these storms? And what's shown in the image there is a very famous picture from a paper nearly 100 years ago that condensed decades of work done by a bunch of very smart Norwegians based in Bergen, and compiling surface observations to understand the structures of these storms. If you're in Scandinavia, come on shore off the North Atlantic and produce your weather. These are the weather makers for the mid-latitudes, these extratropical cyclones or low pressure systems. And they're characterized by low pressure, counterclockwise circulation. But the key discovery from that Norwegian group was the importance of fronts, a term they invented because the world was at war when they were doing this work, and they thought of fronts. And there's warm fronts and cold fronts, as indicated in the diagram. And that's where the weather, the rainfall, is concentrated in these storms. And so that was really their key contribution. The energy from these storms, as I just indicated, the primary energy comes from these storms, as was realized back by the Norwegians, from the temperature gradient in the atmosphere. That creates gravitational potential energy that these storms can extract. But secondarily, but also very, very important, is the latent heat released when precipitation forms. And that's concentrated in these fronts, and that's going to prove important later because these fronts are fairly small spatial scale features that global climate models have difficulty capturing at their typical 100-kilometer or coarser resolutions. So let's go on to the next slide, Jimmy. Right, so this is really, the storms are organized in these storm tracks. And a classical way to look at the storm tracks, and the way that Tim was looking at them, is to track the center of the low. And people have been doing this for a long time. This is a remarkable diagram from a geography textbook in the 19th century. And it basically captures the key features. The storm activity, although it looks like they've mixed in some tropical cyclones there as well, the Atlantic. But storm activity is concentrated in the very strong temperature gradients on the east coast of the continent. So in the wintertime, you have cold air over the land. The ocean is kept warm because of its heat capacity, and warm water being brought up from the subtropics by western boundary currents like the Gulf Stream and the Kuroshio, and that's where storm activity tends to concentrate. Well, I guess we can go on. So if you're a climate dynamicist, large-scale dynamicist like I am, the I get excited by these storms because of their contribution to the global heat engine of the atmosphere that creates our climate and sets the dynamical context for our climate. And what storm tracks do is these storms, and in the storm tracks, is they transport heat from the subtropics to the polar latitudes. So looking at the global circulation, we could have put that slide in here. We didn't. Coming out of the tropics is this thing called the Hadley cell. It's an overturning circulation, moves heat out of the equatorial regions into the subtropics to get the heat from the subtropics poleward from there to balance the radiative deficit that you have at high latitudes with more heat going out by infrared radiation than solar radiation coming in. The mechanism that balances the heat budget is the heat transport by these mid-latitude cyclones. And what you're seeing here is a diagram that shows how that northward heat transport is concentrated by those red colors and concentrating in the northern hemisphere in those northern hemisphere storm tracks. Go on. The other thing that's important for these storm tracks is that there's, in the outside the tropics, that's where rainfall is concentrated. And we know that when a low pressure system comes over our town in the mid-latitudes, Raleigh, North Carolina, New York City, wherever, we get rain or snow sometimes. And actually that precipitation signal is even stronger over the ocean where there is more moisture available. So there's two important things about that. One is that we care about these storms from a weather forecasting point of view because they make it rain or snow. And the other thing is that rain or snow falling in these storms is contributing to the energy of the storm, to the deepening of these extratropical cyclones, as Tim alluded to earlier. So I think it's over to you now, Jimmy.
Okay, thanks. And now what we're going to do is very similar to what Tim did, where we're going to talk about how ingredients that affect the strength of the storms are projected to change in the climate models. And the three main processes that affect the storms are the equator to pole temperature gradient, and that is expected to decrease. And so the way we can visualize that here is in the bottom left panel. This is height versus latitude, so northern hemisphere, looking at temperature. In the contours, it's the climatology, and in the color shows the projected change in temperature. And it's showing the end of the 21st century minus the 20th century, and where it's orange near the surface, near the pole, you can see there's more warming than what's happening in the mid-latitudes or in the subtropics. And so this is a visualization of the zonally averaged decrease in the meridional temperature gradient. And remember, this is the primary ingredient for the dry mechanism behind the strength of these storms. And then bullet point 2 is the increase in low-level atmospheric water vapor. And as Walt was just discussing, that is associated with strengthening the storms. And the panel on the bottom right is showing a similar type figure, but instead of temperature, this is the specific humidity, so a measure of the water vapor in the air. And there, what you can see is across all latitudes, there's an increase in the amount of water vapor in the 21st century. So again, the color shading is what you want to focus on. So that's 21st century minus 20th century. So now we're thinking, okay, so we'll have a decrease in baroclinicity, which should weaken the storm, but that competes with an increase in the availability of water vapor, which could strengthen the storms. Talking about the strength of the storms here, I'm going to talk about a couple different metrics for it, but generally you think about that in terms of wind strength. Bullet point 3 mentioned something that David brought up in his question for Tim, which is the actual lapse rate is moving closer to the moist lapse rate, meaning things are more stable. And this, the response of the storms to this change is the least studied aspect of this problem, I'd say. And this is probably because we still don't have a great handle on, in the current atmosphere, how important, or if any, the role that vertical stability actually plays in these storms. I have a PhD student who's working on that right now. All right, so the idea of diabatic heating strengthening the storms has been known for a while, and there was a series of interesting IOPs, so intensive, what is it? Well, anyway, field campaigns in the 80s because of rapidly intensifying extratropical cyclones, which were given the name bomb storms. And what we're looking at here is synoptic maps taken from a numerical forecast model where it wasn't a forecast, it was a hindcast of a storm. And in this case, the storm is approaching the northwest US, so you can barely make out in dashed lines Oregon and Seattle in the top right corner of these maps. And then the contours are showing sea level pressure, which Tim was just talking about can be used as a metric for the strength of these storms, provided that you're looking at a fixed latitude. And in this case, the idea is that on the left, in the control storm, you can see the number of closed contours is much larger than on the right. And in fact, they label the center of the storm. So the control has this number 969. So that's 969 hectopascals, indicating the depth or the central low pressure. And on the right, in the dry case, so in a numerical weather model where they don't allow any condensation or any other kind of latent heating associated with water vapor or water to occur, you can see the center pressure is 989 hectopascals. So we've known a while now, especially for storms over the water, the processes associated with the water itself are important for the strength of the storms. So what we did more recently was attempt to do a very clean study where we actually take a numerical weather model, but instead of using an actual hindcast conditions, set up a idealized condition so that we have control over all aspects of the development of the storm in terms of the initial conditions and the boundary conditions. And the reason you really want to do this is because the mid-latitudes have so much interannual variability and internal variability on seasonal timescales that when you look at one storm versus another, it's hard sometimes to pinpoint what's causing the change. In this case, we were interested in the strength of the storm in terms of its winds. And on the left, we characterize that using the eddy kinetic energy. So that's the winds integrated over the entire circulation of the storm without accounting for the initial state. And the color in this slide is showing you, on the left is showing you how much initial relative humidity we allow there to be in the model. And so in the blue case, we have a very dry model. And in the red case, we have relative humidity, initial condition relative humidity that's more water vapor than even what's seen in the current atmosphere. And what your eye should be drawn to is that the peaks of these curves increases with height, and the timing of the peak occurs earlier. So the availability of the water vapor both strengthens the overall intensity of the storm and also allows the storms to intensify faster. On the right, we were interested in asking the question, okay, how does this impact of the water vapor change depending on the resolution that we run the model? Because it's been mentioned earlier that these climate models oftentimes are run at coarse resolutions that don't capture all of the physics that go on within the storms. And here we actually start at a 200-kilometer resolution, so that's the blue lines, and then ramp up to a 25-kilometer resolution, which is the red line. And at 25-kilometer resolutions, we are not even approaching the resolution that current numerical weather models are run. This instead was asking the question about climate models that we might expect to exist in the near future. And in this case, what you can see is comparing the dashed versus solid lines. The dashed lines are the dry model runs. Solid lines are model runs with water vapor. In every case, regardless of resolution, there's an increase in the intensity of the storm, and the storm intensifies faster when water vapor is present. It's interesting to note, however, the relative changes differ in these for the different resolutions. And that actually leads us into the next study that we're going to summarize. And in this case, they were looking at a similar idea. However, they were focused in more detail on the physics of what was changing within the storm. So now on the left, we're comparing two numerical model runs, one at 120 kilometer resolution and one at 20 kilometer resolution. So 120 kilometers is probably what we'll see in the next CMIP experiments, whereas the 20 kilometer resolutions is coarse resolution for a numerical weather model. The color in this figure is showing the heating associated with diabatic processes. And the main diabatic process when you're sitting at about 700 hectopascals is going to be condensation associated with ascending warm and moist air that then generates precipitation. And what you can see is the difference between the two panels is there's a lot larger amount of diabatic heating when you go to higher resolutions. Related to that, if we now shift our focus to the right side and we look at the difference in the intensification of the storm, and in this case it's done by looking at a diabatic height tendency, so the change in the geopotential height with respect to time due to the diabatic heating, you can see that the 20 kilometer run has a much greater impact from the diabatic heating than the 120 kilometer run. So this paper by Jeff Willison was meant to indicate to the community that, okay, so as we're thinking about and interpreting what the climate models are showing for changes in storms, we have to keep in mind that the climate models are missing or underestimating one key factor in the storm intensification simply because of their resolution. Building on that idea, if we look at the storm tracks rather than an individual storm, so the same metric that Walt introduced earlier, where we say, all right, now let's integrate the effect of the storms and include cyclonic and anticyclonic activity in this metric by simply looking at the variance of synoptic frequency variability. And in this case, it was variance in synoptic frequency variability of meridional wind. So how much north-south motion do you have on timescales of 2 to 8 days? And in that case, you can look at the color shading to see the difference between the 20 kilometer model run and the 120 kilometer model run. And everywhere where it's orange and red, you know that the 20 kilometer model run is showing a more intense storm track. And we can associate that with the diabatic heating that's going on, because what they're doing on the right panel is saying, okay, now on top, let's look at the 120 kilometer resolution and ask how much of the storm track is being intensified by diabatic heating. And then on the bottom panel saying in the 20 kilometer resolution, how much is the storm track intensifying due to diabatic heating? And you can see that there's a significant impact from the diabatic heating. And in the paper, they go in and they calculate the relative contributions of the diabatic heating. And it was the leading term in terms of what changed the strength of the storm tracks in the 20 kilometer run as compared to the 120 kilometer run. I'll take this moment to also point out, so on the right panel, they show the label says 850 hectopascal V prime T prime. So in that case, they're looking at the meridional heat transport associated with the 2 to 8 day eddies. And you can see that the meridional heat transport on the right, which you could maybe focus on the contours, looks pretty similar to the meridional wind variance, which is the contours on the left. And so this storm track, there are different metrics you can use that typically give pretty robust results in terms of the general pattern of this behavior. Next, we'll jump to, okay, so we've used idealized models and seen that we expect some change, and the GCMs might not capture things perfectly. What do the GCMs show us in terms of impacts? And so this study by Lennart Bengtsson examined 4 GCMs from examined GCMs from the CMIP-5 archive and asked the question, okay, so can we look at how the surface winds change in the 21st century versus 20th? And anywhere where it's red, the surface winds were stronger, and anywhere it's blue, the surface winds are weaker. And we included this figure to show that in the northern hemisphere, it's actually it's a noisy signal where there's mixed results in terms of how winds change. In the southern hemisphere, so the bottom row, in DJF, you actually see something more indicative of a poleward shift in the storm tracks, because there's intensification near the I think that's the 55 or 60 north latitude or 60 south latitude. It's all red around there, but then it's all blue around that, and that's suggestive of a shift of the storm tracks. For the southern hemisphere in June, July, August, it looks to be more of an intensification. If instead of looking at winds, we look at precipitation, again, the red is more precipitation with a warmer world, and blue is less. And there you can see in the mid-latitudes, for the most part, excluding JJ summer in the northern hemisphere, things are getting wetter everywhere. And a study that came out after we put this chapter together tracked the individual cyclones and showed that this increase in precipitation is associated almost 100% with the change in water vapor rather than with the change in circulation in the storms.
Okay, I guess it's
now. I think I'm handing off to you, Walt.
Yes. So one of the messages hopefully you've gotten from this is that perhaps the global climate model scale is not sufficient to resolve what's happening in these extratropical cyclones, and maybe then misrepresenting their sensitivity to global warming. So that was what was done in this study. Jeff Willison was a PhD student here at North Carolina State, and here you're looking at the differences of a future climate minus a past or current climate, and the strength of the storm track. This is in the upper panel. On the left side is the typical, or maybe even a pretty good, global climate model grid scale. And on the right is a grid scale that, as Jimmy points out, would not be so great for a forecasting model, but is well past the grid scale that we're seeing now in our current climate models. And what you're seeing there is, focusing on the deeper redder colors, this is the kinetic energy in the storm tracks in the upper troposphere, that it gets stronger with climate change on the east side of the Atlantic, so we would say maybe the jet exit, and that intensification is much higher at when the model has better resolution, presumably resolves the fronts and low-level jets and so on in the storms better than what you would get at a GCM scale. Going back to what the storms do for the general circulation, we see a similar picture. The heat transport is interesting because the weakening of the baroclinicity leads to less heat transport on the west side of the Atlantic, northwest Atlantic. But on the east side, heading into Europe and the British Isles, you see more heat transport in a future climate, presumably because the storms are stronger, presumably they're stronger because they're extracting more latent heat from a moisture atmosphere. But once again, we see that effect is stronger at the higher resolution. Now these things, key point here is these were all done in a limited area model. Basically, you're seeing the domain of the model in that box, roughly. So unlike a global model, if these storms transport more heat poleward, that doesn't change the global climate in this model. The global climate cannot respond in these limited area models. So while on the one hand, we could say the GCMs may be missing things because of their grid scale, these limited area models are missing feedback processes because they are limited area models. So if we go on to the next, going from the storm tracks to particular storms, this was work done by a master's degree student here. Yes, I'm blanking on Marciano's first name, but anyway, he studied particular storms. We selected some characteristic storms that had occurred, showed that the model, this is again a limited area model, weather research and forecasting model, or WRF, forecast or simulated, hindcast I should say, simulated the storms pretty well compared to what happened. And then we do this technique that's called pseudo-global warming, where we put into the model global warming conditions, warmer sea surface temperatures, warmer continent, weaker temperature gradient, and in fact, we even change the greenhouse gas levels. And we get those temperature patterns, the pseudo-global warming, we call it pseudo because this model doesn't produce the warming. We get that from a global climate model, and then sort of downscale it into this local model. And what you see are some increased deepening with the future conditions. You can see that the red line, over time, this on the right, the storms get deeper on average on the future conditions. And when you follow that out, and then you see all each individual storm, so you're seeing the difference between future minus current deepening, and almost all the storms, these are strong weather bringing storms to the East Coast. All those storms we would project would be stronger in the future. And once again, they are responding to these competing effects of reduced baroclinicity, but more latent heat from warmer ocean. So we go on to the next slide. If you dig down to what's actually happening in the storms by doing a composite, what's done is compositing the storms during a period in which they're deepening rapidly. So you're moving a block, that block that you see at the top with the storm. And at the top left and right, you're seeing the precipitation in millimeters. And with the storm center being, the center of the lobe being where that asterisk is. And so very, very clearly, warmer water, it's basic physics, Clausius-Clapeyron equation, if you will, gives you more precipitation in a given dynamical storm if the ocean is warm, or if the conditions are warmer. So that's what's shown in the top. You go to the bottom, we have this quantity which those of us in atmospheric dynamics much love, called potential vorticity. And it's basically telling you something about the tendency of the air to spin cyclonically or spin counterclockwise, which of course is what happens in a low pressure system. And that potential vorticity in low levels is actually created, and we can show this dynamically, it's created by the latent heat that's released in the mid-levels of the atmosphere when water vapor condenses. And that potential vorticity at low levels, that tendency to spin cyclonically, is stronger and more concentrated in those future storms because there's more latent heat, because the atmosphere is juicier, because the surface is warmer. I think we can go on.
All right. So
back to you.
The hand pass back. Thank you. All right. So finally, we'll wrap up a little bit with questions of what the GCMs show in terms of the location.
Okay. It's
Okay. Am I talking? Okay. Sorry. So the strength of or the location of the strongest intensifying storms on the East Coast. So this study used the CMIP archive, followed the approach that Tim outlined of tracking individual tracks, found the individual tracks in a lot of CMIP-5 models, and then separated out those that intensified the most rapidly, and then said, okay, let's look at the location of these storms in the future climate versus the present climate. And so where it's yellow-orange, that's where in a future climate, the model projections predict increase in the frequency of the strongest intensifying storms. And so what you see here is a shift in the location. Instead of the strongest intensifying storms occurring right off the coast, this is suggesting they're intensifying along the eastern seaboard. So this is not to say that the intensity in this region for the storms increases. This is saying the rate at which they deepen is strongest in this region, and there's more of them there. So I think in terms of impacts, it's hard to say whether this translates to impacts. And speaking to Brian Colley about this study, he agreed with me that this is the amount of time they're using in this is right on the edge of being a long enough period of time to where they're averaging over multiple INSO cycles and limiting the influence of things like slow frequency changes in the NAO. So this signal is, I would say, a slightly defensible signal, but I'm very cautious in this regard when I see signals like this. So I would say I would put this one at 51%. I'm going to skip this next slide in the interest of time. This overlaps nicely with things that Tim had already said, and just go to the final slide. And so here we just want to emphasize that changes in mean temperatures and winds, moisture, so the globally average changes and hemisphere average changes are mostly understood, but there's uncertainty in these storms, in the changes in the intensity of these storms in terms of winds because of competing effects. And I would say there's not uncertainty in terms of precipitation in these storms. I think these storms are going to get wetter no matter what. But there is strong variability in the climate system that affects the path of these storms. And so on that one, Walt and I are both still of the feeling that, okay, well, we need to look at very long time averages for things like the path of the storms to put much faith in something as being a signal driven by global warming. And then our final bullet point is, if we were to turn this into something where we would go to folks in New York City and the Emergency Hazard Management Office and say, okay, here's the action items you can take in terms of storms and storm track, I would say there's not yet a lot in hand that we can take actionable items on. But when I talk to the folks in the emergency management offices, I tell them that the biggest impact of these storms for New York City is the snow and the storm surge. And on the snow, Judah pointed out there's multiple papers that show we're definitely going to get less snow overall, but more likely than not, the really intense snowstorms are going to continue to occur. And then as far as storm surge, because sea level rise is such a big issue, that the changes in these storms is probably secondary to what the action items should be in terms of planning for that. And so with that, I'll conclude. Thanks for your time.
Walter, Jimmy, thanks very much for that very smooth baton passing back and forth and very informative presentation. I have a question which is sort of similar to the question I asked Judah. You show very convincingly that even at the finest scale currently utilizable for climate models, they underestimate the intensity of the diabatic heat release associated with fronts in storms, and therefore underestimate, for example, potential changes in storm intensity as climate warms. Do you have any idea what is it exactly about the resolution effect, the finer resolution allowing for more diabatic heating? Is it that there's, on a finer resolution, greater convergence of moisture? Is the convection scheme more appropriate at finer resolution? What are models doing wrong at the coarser resolution that maybe they can parameterize better if it comes to that?
Well, I'll take a first cut and then I'll let Jimmy see if he agrees. So my thinking on this is very much informed by my colleague here at NC State, Gary Lackman. And so Gary talks about the the features in the storms that bring moisture, that converge the moisture, which David just mentioned, into the regions in which it gets released. So the low-level jets in the storms, or the warm conveyor belts, these are not, to use jargon, they're not large-scale features, they're mesoscale features. And I think they're just missed. If you look at the distribution of moisture flux in a storm, it's as you resolve it better and better, and Jimmy's probably done this more than I have, what you see is that gets much more interesting and much more robust as you go to finer scale. So what you're missing is the covariance, if you will, of the strong flow into the storm and the high moisture. And then that matters because it feeds back, because that strong moisture flux into the storm, the latent heat release makes the storm stronger. So there's a positive feedback that makes the well-resolved storm diverge from a less well-resolved storm. Jimmy, you want to comment?
Yeah, no, I totally agree. I think we need to start. It's interesting evolution, because in class at work about warm conveyor belts, like the Keith Browning schematic, the warm conveyor belt is a nice broad arrow in the warm sector, but recent numerical modeling studies show that the warm conveyor belts are actually very thin filaments, spatially thin. And so the models at their resolution aren't able to get these tight regions of really large amounts of moisture flux. And then the other thing to remember is the feedback on the circulation is associated with the vertical gradient in the heating, not the heating itself. And so you can, if you lay out that heating in the GCM, especially around 600 hectopascals, you're doing that in an area where the model has the widest vertical spacing. And so I think the vertical resolution might be one of the shorter term things we can work towards kind of trying to help with this issue.
Great, thank you. And as you know, we now are working on a finer vertical resolution model. So perhaps you might be interested in taking a look at it and seeing if it is doing any of these things better.
Yeah, no, it's a great idea.
Sounds good.
Great. This is Cynthia. I want to first thank the speakers. They were all fantastic talks today, this afternoon. Walt and Jimmy and Judah and Tim, thank you all. And the talks really fit together really well, so it was great. We also want to thank all the people who listened in. And yes, and we now record every one of these talks, and they'll be available on the CC Run, right, Dan?
Yes.
The CC Run, which is the NOAA RISA run from Columbia, so that people can then review them and they can and use them in their classes. So, but thanks also to all the audience. If you have any further questions, just send them in. We'll get them to the right the right presenters, and we'll keep going. And then next time,
The next talk is January 15th.
And do we know who it is?
I don't know.
We can't remember. We don't remember who it is.
But we'll send out.
We'll send out
information well in advance, and hope you can all join then.
Yes, good.
Thanks again very much, guys.
Yes, thank you to the presenters.